And now we come to one of my personal favourite bits of mathematics, volumes of solids of revolution. I just think it's a really clever application of integration. Let me show you. What I'm going to do is take this function and I'm going to rotate it either around the x-axis or around the y-axis. I'm going to look at the shape I get. Here's what I'm rotating around the x-axis. Here's the same curve but rotated around the y-axis. What solid shape do I get when I do that rotation? Did you guess right? If I take this piece of it from the original function and I rotate it into a solid, I'm going to get a shape like this. If I take the same curve and rotate it around the y-axis, I'm going to get this shape. And our job is going to be to work out the volume of that shape. What's the volume of that shape there? So let's get started. Here's how this method works. Whatever my function f of x is, I'm going to take slices of it, slices through the shape that's formed by the rotation. The shape of each of those slices is a circular disc. It's a circle whose thickness is delta x. Well, in the limit it's going to become dx. So what I'm going to do is I'm going to find the volume of this shape by adding up the volumes of all of the little pieces along the way. Well, what's the volume of this cylindrical piece here? Well, it's the area of the circle times by the height of the cylinder. The area of the circle is pi r squared times dx. But the radius r is my f of x. So the volume I want is integrating from a to b of pi radius squared dx. Equivalently, you can put the pi outside and just think of this as y. Pi y squared dx. And likewise, if you're going to rotate around the y-axis, it's going to become pi x squared dx. Sorry, didn't quite get that right, did I? It's going to become pi x squared dy, because you're integrating along the y-axis. So let's try a simple example. Determine the volume of the solid of revolution when y equals x squared is rotated around the x-axis between x1 and 3. So the first step is always sketch the graph. Get an idea, visualise what's going on. The textbook actually suggests shade in the region that you're rotating. Shade in this bit of the graph here to help you figure out what's the shape I'm going to get. Okay, it's a solid of revolution around the x-axis, so I want the integral from 1 to 3 of pi y squared dx. Integral from 1 to 3 of pi y squared dx. They've just shifted the pi out. Well, this is actually a fairly simple integral. So y squared is going to be x squared squared. X squared squared, which is pi integral of x to the 4th dx. Well, x to the 4th is 1/5 x to the 5th. Plug it in at 3, plug it in at 1, subtract. And there's your exact answer. What about if I'm rotating around the y-axis? Determine the volume of the solid of revolution when the curve x squared plus 2 is rotated around the y-axis, and we're only interested in y values from 2 to 4. Now, they didn't actually have to tell us x greater than or equal to 0. If I'm rotating around the y-axis, I'm only interested in one part of that curve. Okay, so I'm interested in this bit. What happens when I rotate it? Well, I know I'm going to be looking for the integral of x squared, that's my radius, integral of x squared dy. There's a trick here. You don't have to do quite as much as the book did. So y is x squared plus 2. So there's y is x squared plus 2. Well, in that case, x squared is y minus 2. Now they've simplified this into the square root, but you don't actually need x. You know you're about to substitute x squared, so you can actually stop here. You don't have to work this out, because you can simply go, the volume I want is pi x squared dy, and then substitute x squared as y minus 2 and go directly to this line. I'm integrating with respect to y, so this is relatively straightforward. Half y squared minus 2y. Put in your values and subtract, and there's your exact answer.